Before, we've used things that looked like classes, but they didn't say class on them, they said struct on them.
Yes, and so what is that? And so, so let's play a little game. And so let's talk about this idea of values and references, because that's what struct versus class really means in Swift. A value is a struct thing, and a reference is a class thing. And so let's talk about Python. Here's some really simple Python code, and there's no tricks here. What we're doing is we're assigning 4 into A, we're copying A into B, we're incrementing A and printing them out. And so when you do this, you see that A gets incremented, of course. B does not, of course. This all makes perfect sense. In Swift, you do the same thing, you get the same thing out. Right? This is how math works, right? All very straightforward. Let's talk about arrays. So here I have an array or list in Python, and I put into X, and then I copy X into Y. I add something to X, and it has it. I have to point with this. So, and then it has the extra item. That makes perfect sense, right? But what happens to Y? What? What just happened here? I just added something to X, and now Y changed? Now what is going on here? Well, we learn that there's this thing called a reference, and we learn that it does things like this, and we learn when it bites us. What happens in Swift? Well, Swift has arrays. It doesn't have lists the same way. And so here we have, again, it's identical code except var. We put in 1 and a 2 into X, we copy X into Y, we add something to X, we print it out, we get the extra element. But Y is correct. What just happened? So this is something called value and reference semantics. And in Swift, arrays, dictionaries, tensors, like all these things have what's known as value semantics. And let's dive in a little bit about what that is. So a value in something that has value semantics is a variable that, sorry, this is self-referential. When you declare something in your code, you're declaring a name. And if it's a name for a value, that name stands for that value. Right? X stands for the array of elements that it contains. This is how math always works. This is what you expect out of basic integers. This is what you expect out of basic things that you interact with on a daily basis. Reference semantics are weird, if you think about it. So what we're doing is we're saying that X is a name for something else. And so we usually don't think about this until it comes around to bite us. And so this is kind of a problem. And let's dive in a little bit to understand why this causes problems. So here's a function. It's doThing. It's something that Jeremy wrote with a very descriptive name. And it takes T, and then it goes and updates this, and that's fine, right? It's super fast. Everything is good. You move on and put in a workbook, and then you build the next workbook. Next workbook calls into doThing, and you find out, oh, well, it changed the tensor I passed in, but I was using that tensor for something else, and now I've got a problem because it's changing a tensor that I wanted to use, and now I've got this bug, I have to debug it, and I find out the doThing is causing the problem, and so what do? I go put a clone in there. I don't know who here adds clones in a principled way, or who
I do use it in a principled way. So what we do in FastAI is we kind of don't have clone, and then when things start breaking, I add clone until things stop breaking, and then we're done.
That sounds great.
Yeah, so there's a lot of clone in FastAI, and yeah.
That's a good principle.
Possibly there's the right number, or possibly a few too many, or possibly a few too few.
Well, so now think about this. What we have is we have a foot gun here in the first case. So something that's ready to explode if I use it wrong. Now I added clone, and so good news, it's correct but slow. Like, so it's going to do that copy even if I don't need to, which is really sad. In Swift, things just work. You pass in a tensor, you can update it, you can return it, and it leaves the original one alone. Arguments in Swift actually even default to constants, which makes it so that you can't do that. If you do actually want to modify something in the caller, you can do that too. You just have to be a little bit more explicit about it and use this thing called in-out. And so now if you want to update the thing somebody passed to you, that's fine, just pass it in-out, and everything works fine. And on the call side, you pass it with this ampersand thing so that they know that it can change. Now, what is going on here, right? So this is good math. This is like the correct behavior, but how does this work? Well, we were talking about names, we were talking about values. And so here I have a struct. This is a value-y thing. And so I say it has two fields, a real and imaginary, and I define an instance of my complex number here named x. And so this is saying I have x, and it's a name for the value that has 1 and 2 in it. And so if I introduce y is another notational instance of this struct. And so it also has a 1 and a 2. And if I go and I copy it, then I get another copy. And if I change one, then I update just y's. Right? This is, again, the way things should work. And so this works with structs, this works with tuples, this works with arrays and dictionaries and all that kind of stuff. How do references work? Well, references, the name here I have a class, and the class has a string and it has an integer. And so somewhere in memory, there is a string and there is an array, and they're stuck together, just like with a struct. But now when I say x is actually a reference or a pointer or a
just to be clear,
indirection.
The reason for that is because you wrote class instead of struct. So by writing class, you're saying, when you create one of these things, please create a reference, not a value.
Yes, that's exactly right. And now what happens with references is you now get copies of that reference. And so when I copy x into y, just like in PyTorch or Python, I have another reference or another pointer to the same data. And so that's why when you go and you update it, so I'm going to go change the array through y, it's also going to change the data that you see through x. Right? And so in Swift, you have a choice. And so you can declare things as classes. And classes are good for certain things. And they're important and valuable, and you can subclass them. And classes are nice in various ways. But you have a choice. And a lot of things that you've seen are all defined with structs because they have much more predictable behavior and they stack up more correctly.
So in this case, I was trying to literally duplicate a Python/PyTorch API. And so I just found I wasn't able to unless I used class.
Yes.
But then you kind of said, okay, well, that's how you do it, but...
Yeah, and we'll get back to autodiff in a second.
But don't do it that way.
Yeah, and so you can absolutely do that. And again, when you're learning Swift, it's fine. Just reach for the things that are familiar, and then you can learn as you go. That's perfectly acceptable. But here we're trying to talk about things Swift is doing to help save you and make your code more efficient and things like that.
And I still reach for class a lot. But then every time a real Swift programmer takes my thing that had class and replaces it with something more Swifty, it ends up being like shorter and easier to understand. And so like I agree, like go for it, get things working with class. But
when it becomes time, start to work with this and look at it and figure out how it works. Now there's one thing that's really weird here. And if you remember last time, the first thing I told you about was var and let, right? And what is going on here? This does not make any sense. We've got y, and now we are updating, if this thing will go away, we are updating a thing in y even though y is a constant. And what does that even mean? Well, the reason here is that the thing that is constant, is this reference. And so we've made a new copy of the reference, but we're allowed to copy the thing it points to because we're not changing x or y itself, right? So this doesn't make sense. None of this makes sense. But how does let and var work? Well, this is a thing that comes back to the mutation model in Swift. And I'll go through this pretty quickly. This is not something you have to know. But let's say I have a complex number and it's a struct. And I say, hey, this thing is a constant. I want to go change it, right? That's not supposed to work. What happens? Well, if you try to do that, Swift will tell you, haha, you can't do that. You can't use plus equals on a real that's in a C because C1 is a let. And Swift is helpful, and so it tries to lead you to solving the problem. It says, hey, by the way, if you want to fix this, you want to make it go away, just change let to var, and then everything is good. That's totally fine. Now, okay, fine. Well, maybe I really do want to change it. And so what I'm going to do is I'm going to get a little bit trickier, and I'm going to define this extension. I'm going to add a method increment to my complex number. I'm going to increment it inside the method, and then call the method. Can I get away with that? Well, these things may be in different files. The compiler may only be able to see one or the other. And so if you run this, it has no idea whether increment's going to change that thing, right? And so what the compiler does is it says, well, you can't increment real inside of this increment method either, because it says self is immutable. And it says mark method mutating to make self mutable. Now, the thing to think about in methods, both in Python but also in Swift, is that they have a self. Right? In Python, you have to declare it. Swift has it too. It's just not making you write it all the time because that would be annoying. And so when you declare a method on a struct, what you do is you're getting self, and it's a copy of the struct. Okay? Now, what this is saying that, hey, you're actually changing self.real. Self is constant, and so you can't do that here. But what you can do is you can mark it mutating. And so what that looks like is that says, we can mark this function as mutating, and what that does is it says, our self is now one of these in-out things, the in-out thing that allows us to change it in the caller. And because it's now mutating, it's totally fine to change it. That's no big deal. And the compiler leads you to this and shows you what to do. But now we come back to this problem over here. We say, well, we have a constant, we're calling increment. How does that work? Well, it still doesn't. The compiler will tell you, hey, you can't do that. You can't mutate C1. And now it knows the increment can change it. And so it says, really, 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 if you want to do this, go mark C1 as a var. And Jeremy would say, just mark everything as a var, because
pretty much
that's how he is. And so the nice thing about this, though, is that it all stacks up nicely and it all works. And this is what allows, this is kind of the underlying mechanics that allow the value stuff to work. Now, you may be wondering, how is this efficient? So we were talking about in the PyTorch world, you end up copying all the time, even if you don't end up needing it. In Swift, we don't want to do all those copies. And so, on the other hand, we don't want to be like always copying. So where do the copies go and how does that work? So if you're using arrays, or arrays of arrays of arrays of dictionaries of arrays of like super nested things, what ends up happening is array is a struct. You might be surprised. And inside of that struct, it has a pointer or a reference. And so the elements of an array are actually implemented with the class. And so what I have here is I have A1, which is some array, and I copied it to A2, and I copied it to A3, I copied it to A4 because I'm passing it all around. I'm just passing this array around, no big deal. And what happens is I'm just copying this reference, and it happens to be buried inside of a struct. And so this passing around arrays, full value semantics, super cheap, no problem. It's not copying any data, it's just passing the pointer around, right? Just like you do in C or even in Python. The magic happens when you go and you say, okay, well, I've now got A4. And so all these things are all sharing this thing. I'm going to add one element to A4. Well, what happens? Well, first thing that happens is append is a mutating method. And so it says, hey, I'm this thing called a copy on write type. And so I want to check to see if I'm the only user of this data. And it turns out no, lots of other things are pointing to our data here. And so lazily, because it's shared, I'll make a copy of this array. And so I only get a copy of the data if it's shared and if it changes.
So that should be 1, 2, 3, 92?
Yeah, that should be 1, 2, 3, 92. I am buggier than Swift. Now, the interesting thing about this is because of the way this all works out is if you go and you change A4 again, it goes and just updates it in place. There's no extra copy. And so the cool thing about this is that you get exactly the right number of copies, and it just works. You as a programmer don't have to think about this. This is one of the things that Swift is just like subtracting from your consciousness of the things you have to worry about, which is really nice. And so a really nice aspect of this is that you get algebra, like values work the way values are supposed to work. You get super high performance. We get to use more emojis, which I always appreciate. If you want to learn more about this, because this is also a really cool, deep topic that you can geek out about, particularly if you've done object-oriented programming before, there's a lot that's really nice about this. There's a video you can see more. So let's go back to that autodiff thing. And let's actually talk about autodiff from a different perspective. So this is the autodiff system implemented the same way as the manually done PyTorch version. And we didn't like it because it was using references. Let's implement it, again, the very low-level manual way in Swift. But before we do, let's talk about where we want to get to. So Swift has built-in, and Swift for TensorFlow has built-in automatic differentiation for your code. So you don't have to write gradients manually, you don't have to worry about all this stuff. And the way it works is really simple. There are functions like gradient, and you call gradient, and you pass it a closure, and you say, what is the gradient of x times x? And it gives you a new function that computes the gradient of x times x, and here we're just calling that function on a bunch of numbers that we're striding over and printing them out, and it just gives you this gradient of this random little function we wrote. Now, one of the interesting things about this is, I wrote this out, it takes just doubles or floats or other things like that. Autodiff in Swift works on any differentiable type, anything that's continuous, anything that's not like integers, anything that has a gradient. And so
you can't do this in just a library. This has to be built into the language itself because you're literally compiling something that's multiplying doubles together and it has to figure out how to get gradients out of that.
Yeah, you can do things as a library, and that's what PyTorch and other frameworks do in Python,
but
it doesn't work the same way at all.
PyTorch will not do that on doubles. PyTorch
yes,
requires you to do that on tensors.
Yes. And so this doesn't just work on doubles. If you want to define quaternions or other cool numeric scientific-y things that are continuous, those are differentiable too, and that all stacks out and works. So there's a bunch of cool stuff that works this way. You can define a function, you can get the gradient at some point with the function, you can pass enclosures, like all this stuff is really nice. Instead of talking about that, we're going to do the from the bottom up thing. And so I'm going to pretend I understand calculus for a minute, which is sad. So if you think about what differentiation is, computing the derivative of a function, there's two basic things you have to do. You have to know the axioms of the universe, like what is the derivative of plus, or multiply, or sine or cosine, or tensor matmul. Then you have to compose these things together. And the way you compose them together is this thing called the chain rule. And this is something that I relearned, sadly, over the last couple of weeks.
And that we did in the Python part of this course as
yes.
well. And we wrote it a different way. We had y dx equals to y du dx.
Yeah, apparently there's some ancient feud between the people who invented calculus independently, and they could not agree on notation. Whatever. So what this is saying if you want the derivative of f calling g, the derivative of f calling g is the derivative of f applied to the forward version of g multiplied by the derivative of g. And this is important because this is actually computing the forward version of g and in order to get the derivative of this. And
which we kind of hid away in our y du dx version.
Do you want to make the font larger?
Sure. I don't know how to do it on your machine. Oh, there you go. So how are we going to do this? Well, what we're going to do is we're going to look at defining the forward function of this. And so we'll use the mean squared error as the example function. This is a little bit more complicated than I want, and so what I'm going to do is I'm going to actually just look at this piece here. And so I'm going to define this function MSE inner, and all it is it's the dot squared dot mean. So it's conceptually this thing, MSE inner, that just gets the square of x and then does the mean, just because that's simpler. And then we'll come back to MSE at the end. And so in order to understand what's going on, I'm going to find this little helper function called trace. And all trace does is you can put it in your function, and it uses this little magic thingy called pound function. And when you call trace, it just prints out the function that it's called from. Okay, and so here we call foo, and it prints out, hey, I'm in foo AB, and I'm in bar X. And so we'll use that to understand what's happening in these cells. So here I can define, just like you did in the PyTorch version, the forward and the derivative versions of these things. And so x times x is the forward. The gradient version is 2 times x. X dot mean is the forward. This weird thing of doing a divide is apparently the gradient of mean. And I checked it apparently works. I don't know why. So then when you define the forward function of this MSE inner function, it's just saying give me the square and take the mean. Super simple. And then we can use the chain rule, and this is literally where we use the chain rule to say, okay, we want the gradient of one function on another function, just like the syntax shows. And the way we do that is we get the gradient of mean and pass it to the inner thing and multiply it by the gradient of the other thing. And so this is really literally the math interpretation of this stuff. And given that we have this, we can now wrap it up into more functions, and we can say, let's compute the forward and the backwards version of MSE. We just call the forward version, we call the backward version, and then we can run it on some example data 1, 2, 3, 4.
And just to be clear, the upside down triangle thing is not an operator here, it's just using Unicode as part of the name of that function.
That's the gradient delta symbol thingy. I found that on Wikipedia. So when you run this, what you'll see is it computes the forward version of this thing. It runs square, and then it runs mean. And then it runs square again, and then it runs the backward version of mean and square. And this makes sense given the chain rule, right? We have to recompute the forward version of square to do this. And for this simple example, that's fine. Square is just one multiply, but consider it might be a multiply of megabytes worth of stuff. It's not necessarily cheap. And when you start composing these things together, this recomputation can really come back to bite you. So let's look at what we can do to factor that out. So there's this pattern called chainers, and what we call the value and chainer pattern. And what we want to do is we want to find each of these functions, like square or mean or your model, as one function that returns two things. And so what we're going to do is we're going to look at the other version of calculus's form of this. And so when you say that the derivative of x squared is 2x, you actually have to like move the ddx over with it. And this matters because the functions we just defined are actually only, those are only valid if you're looking at a given point. They're not valid if you compose it with another function.
This is just another way of writing the chain rule.
It's the exact same thing, and so we're going to call this the gradient chain, and all it is an extra multiplier.
And Chris, I just need to warn you, in one of the earlier courses, I got my upside down triangles mixed up as you just did. So
that's not
the
delta.
Other way around is delta, and this one is called nabla, and I only know that because I got in trouble for screwing it up from the survey last time.
Thank you, Jeremy, for saving me. So all this is it's the same thing we saw before. It just has an extra multiplication there because that's what the chain rule apparently really says. So what we can do now is, now that we have this, we can actually define this value with chain function. And check this out. What this is doing is it's wrapping up both of these things into one thing. So here we're returning the value when you call this. We're also returning this chain function. And so now,
can you just explain this TF arrow TF, like how do I read that? Sure. TF arrow TF?
So what this is doing is this is saying we're defining a function square WVC. It takes x. It returns a tuple, right? We know what tuples are. These are fancy tuples like you were showing before where the two things are labeled. So there's a value member of the tuple and there's a chain label of the tuple. The value is just a tensor float. The chain is actually going to be a closure. And so this says it is a closure that takes a tensor float and returns a tensor float.
So that's just a way of defining a type in Swift where the type is itself a function.
Yep. And so what square VWC is going to be is it's going to be two things. It's the forward thing, the multiply x times x, and then it's the backwards thing, the thing we showed just up above that does ddx times 2 times x.
And the forward thing is the actual value of the forward thing. Yep. The backward thing is a function that will calculate the backward thing.
And the chain here is returning a closure, and so it's not actually doing that computation. So we can do the same thing with mean, and there's the same computation. And so now what this is doing is this a little abstraction that allows us to pull together the forward function and the backward function into one little unit. And the reason why this is interesting is we can start composing these things. And so this MSE inner thing that we were talking about before, which is mean followed by square, or square followed by mean, we can define, we just call square VWC, and then we pass the value that it returns into the mean VWC, and then the result of calling this thing is mean.value, and the derivative is those two chains stuck together. And so if we run this, now we get this really interesting behavior where when we call it, we're only calling the forward functions once and the backward function once as well. And we also get the ability to separate this out. And so here what we're doing is we're calling the VWC for the whole computation, which gives us the two things. And here we're using the value. So we got the forward version of the value. And if that's all we want, that's cool. We can stop there. But we don't. We want the backward version too. And so here we call it we call the chain function to get that derivative. And so that's what gives us both the ability to get the forward and the backward separate, which we need, but also it makes it so we're not getting the recomputation because we're reusing the same values within these closures. So given that we have these like infinitesimally tiny little things, let's talk about applying this pattern. I'll go pretty quickly because the details aren't really important. So ReLU is just max with 0, and so we're using the same thing as ReLU grad from before. Here's the lin grad using the PyTorch style of doing this, and so all we're doing is we're pulling together the forward computation in the value thing here, and then we're doing this backward computation here, and we're doing this with closures.
So can I just talk about this difference? Because it's really interesting because, this is the version that Silva and I wrote when we just pushed it over from PyTorch. And we actually did the same thing that Chris just did, which is we avoided calculating the forward pass twice. And the way we did it was to cache away in in.grad and out.grad and n.inner, the intermediate values, so that we could then use them again later without recalculating them. Now, what Chris is showing you here is doing the exact same thing, but in a much more automated way, right?
It's a very mechanical process.
Yeah, so rather than having to kind of
boring.
use this kind of very heuristic, hacky, one-at-a-time approach of saying, what do I need at each point? Let's save it away in something or give it a name, and then we'll use it again later. It's kind of interesting, and also without any mutation,
Yep.
this functional approach is basically saying, let's package of everything we need and hand it over to everything that needs it. And so that way, we never had to say, what are we going to need for later? It just works. So it kind of like, you'll see all the steps are here, out times blah.transposed, out times blah.transposed, right? But we never had to think about what to cache away.
And so this is not something I would want to write ever again manually, personally. But the advantage of this is it's really mechanical and it's very structured. And so when you write MSE, the full MSE, what we can do is we can say, well, it's that subtraction, then it's that dot mean dot squared, and then on the backwards pass we have to undo the squeeze and the subtraction thingy. And so it's very mechanical how it plugs together. Now we can write that forward and backward function, and it looks very similar to what the manual version of the PyTorch thing looked like, where you're calling these functions, and then in the backward version you start out with 1, because the gradient of the loss with respect to itself is 1, which now I understand, thanks to Jeremy. Then they chain it all together and you get the gradients. And through all of this work, again, what we've ended up with is we've gotten a forward and backwards pass, we get the gradients of the thing, and now we can do optimizers and apply the updates. Now,
And can I just mention, like, what Chris was saying about this one thing here and so forth? For Chris and I, we took a really long time to get to this point, and we found it extremely difficult. And at every point up until the point where it was done, we were totally sure we weren't smart enough to do it.
yes,
And so, like, please don't worry that there's a lot here and that you might be feeling the same way Chris and I did. But yeah, you'll get there, right?
this was a harrowing journey.
Yeah, it's okay if this seems tricky, but
Yes.
just go through each step one at a time.
Yeah, but so again, this is talking about the low level mathy stuff that underlies calculus. And so the cool thing about this, though, from the Swift perspective, is this is mechanical, and compilers are good at mechanical things. And so one of the things that we've talked about a lot in this course is the idea of their primitives. They're the atoms of the universe, and then there are things you build out of them. And so the atoms of the universe for tensor, the atoms of the universe for float, we've seen, right? And so we've seen multiply, and we've seen add on floats. Well, if you look at the primitives of the universe for tensor, they're just methods, and they call the raw ops that we showed you last time, right? And so if you go look at the TensorFlow APIs, what you'll see is those atoms have this thing that Swift calls them VJPs for weird reasons. This defines exactly the mechanical thingy that we showed you. And so the atoms know what their derivatives are, and the compiler doesn't have to know about the atoms, but that means that if you want to, you can introduce new atoms. That's fine. The payoff of this now, though, is you don't have to deal with any of this stuff. So that's the upshot. What I can do is I can define a function. So here's MSE inner, and it just does dot squared dot mean. And I say make it differentiable, and I can actually get that weird thing, that chainer thing, directly out of it, and I can get direct low-level access if for some reason I ever wanted to. Generally, you don't, and that's why you say give me the gradient, or give me the value and the gradient. And so this stuff just works. And the cool thing about this is this all stacks up from very simple things, and it composes in a very nice way. And if you want to, you can now go hack up the internals of the system and play around with the guts, and it's exposed and open for you. But if you're, like me at least, you would stay away from it and just write math.
Well, I mean, sometimes we do need it, right? So you'll remember when we did the heat maps, right? To calculate those heat maps, we actually had to dive into the, registering a backward callback in PyTorch and grab the gradients and then use those in our calculations. And so, there's plenty of stuff we come across where you actually need to work with this.
Yeah, and there are some really cool things you can do too. So now we ended up with a model, and so this is something that I never got around to doing the fix me. So here's our forward function. Here we're implementing it with matmols and with the lin function, the ReLUs, and things like that. The bad thing about defining a forward function like this is you get tons of arguments to your function. And so some of these arguments are things that you want to feed into the model. Some of these things are parameters. And so as a refactoring, what we can do is we can introduce a struct, you might be surprised, that puts all of our parameters into it. And so here we have my model, and we're saying it is differentiable. And what differentiable means is it has a whole bunch of floating point stuff in it, and I want to get the gradient with respect to all of these. Okay? So now I can shove all those arguments into the struct. It gives me a nice capsule to deal with. And now I can use the forward function on my model. I can declare it as a method. This is starting to look nicer. This is more familiar. And I can just do math. And I can use W1 and B1. And these are just values defined on our struct. Now I can get the gradient with respect to the whole model in our loss. Right? And all of this is building up on top of all those different primitives that we saw before, that and the chain rule and all these things, that now we can say, hey, give us the gradient of the model with respect to X train and Y train, and we get all the gradients of W1, B1, W2, B2. And all this stuff works. You can see it all calling the little functions that we wrote, and it's all pretty fast. Now, again, like we were just talking about, this is not something you should do for matmul or convolution, but there are reasons why this is cool. And so there are good reasons and there are annoying reasons, I guess. So sometimes the gradients you get out of any autodiff system will be slow because you do a ton of computation, and it turns out the gradient ends up being more complicated, and sometimes you want to do an approximation. And so it's actually really nice that you can say, hey, here's the forward version of this big complicated computation. I'm going to have an approximation that just runs faster. Sometimes you'll get numerical instabilities in your gradients. And so you can define, again, a different implementation of the backwards pass, which can be useful for exotic cases. There are some people on the far research side of things that want to use like learning and things like that to learn gradients, which is cool. And so having the system where everything is just simple and composes but is hackable is really nice. There are also always going to be limitations of the system. Now, one of the limitations that we currently have today, which will hopefully be fixed by the time the video comes out, is we don't support control flow and autodiff. And so if you do an if or a loop, like an RNN, autodiff will say, I don't support that yet. But that's okay, because you can do it yourself. So we'll go see an example of that in 11. There we go. And so what we have implemented here, and we'll talk about layers more in a second, is we have this thing called switchable layer. And what switchable layer is it's just a layer that allows us to have a Boolean toggle to turn it on and off. And the on and off needs an if, right? And so Swift autodiff doesn't currently support if, and so when we define the forward function, it's super easy. We just check to see if it's on, and if so, we run the forward. Otherwise, we don't. Because it doesn't support that control flow yet, we have to write the backwards pass manually. And we can do that using exactly all the stuff that we just showed. We implement the value, and we implement the chainer thing, and we can implement it by returning the right magic set of closures and stuff like that. And so, it sucks that Swift doesn't support this yet, but it's an infinitely hackable system, and so for this or anything else, you can go and customize it to your heart's content.
Yeah, and I mean, one of the key things here is that Chris was talking about kind of the atoms, and at the moment the atoms is TensorFlow, which is way too big an atom. It's a very large atom. But at the point when we're kind of in MLIR world, the atoms are the things going on inside your little kernel DSL that you've written. And so this ability to actually differentiate on float directly suddenly becomes super important, because it means that, like, I mean, for decades, people weren't doing much researchy stuff with deep learning. And one of the reasons was that none of us could be bothered implementing a accelerated version of every damned
Yep.
you know, CUDA operation that we needed to do the backward pass of and do the calculus and blah, blah, blah. Nowadays, we only work with a subset of things that like PyTorch and stuff already supports. So at the point where, you know, so this is the thing about why we're doing this stuff with Swift now, is that this is the foundations of something that in the next year or two will give us all the way down infinitely hackable, fully differentiable system.
Yep. Can we jump to layer really quick? So we've talked about matmul, we've talked about autodiff. Now let's talk about other stuff. So layers are now super easy. It just uses all the same stuff you've seen. And so if you go look at layer, it's a protocol, just like we were talking before. And layers are differentiable. Like they contain bags of parameters, just like we just saw. The requirement inside of a layer is you have to have a call. So layers in Swift are callable, just like you'd expect. And they work with any type that's an input or an output. And what layer says is the input and output types just have to be differentiable. And so layer itself is really simple.
Yeah, and so underneath here you can see us defining a few different layers. So for example, here is the definition of a dense layer, right? And so then now that we've got our layers and we've got our forward pass, that's enough to actually allow us to do mini batch training. And I'm not going to go through all this in any detail other than just to point out that you can see here is defining a model, and it's just a layer because it's just a differentiable thing that has a call function. And you can call the model layer. We can define log softmax. We can define negative log likelihood, log sum exp. Once we've done all that, we're allowed to use the Swift for TS version because we've done it ourselves. And at that point, we can create a training loop. So we'll define accuracy, just like we did in PyTorch, set up our mini batch, just like we did in PyTorch. And at this point, we can create a training loop. So we just go through and grab our X and Y and update all of our things. You'll notice that there's no torch.nograd here, and that's because in Swift, you opt into gradients, not out of gradients. So you wrap the stuff that wants gradients inside value with gradient. And there we go. So we've got a training loop. Now, one really cool thing is that all of these things end up packaged up together thanks to the layer protocol into a thing called variables.
Which layer is differentiable.
Yeah, so
differentiable is also a protocol. Protocols have lots of cool stuff on them.
So thanks to that, we don't have to write anything else. We can just say model.variables minus equals LR times grad, and it just works. Thanks to the magic of protocol extensions, our model got that for free because we said it's a layer.
Yep.
Okay, so I think that's about all we wanted to show there. So now that we've got that, we're actually allowed to use optimizers, so we can just use that instead, and that gives us a standard training loop, which we can use. And then on top of that, we can add callbacks, which I won't go into the details, but you can check it out in 0.4, and you will find that, let's find them, here we go. We'll find a learner class, which has the same callbacks that we're used to. And then, eventually, we'll get to the point where we've actually written a stateful optimizer with hyperparameters, again, just like we saw in PyTorch. And most of this will now look very familiar. We won't look at dictionaries now, but they're almost identical to PyTorch dictionaries, and we use them in almost the same way. So you see we've got states and steppers and stats, just like in PyTorch. And so eventually, you'll see we have things like the LAM optimizer written in Swift, which is pretty great. And it's the same amount of code. And things like squared derivatives, we can use our nice little Unicode to make them a bit easier to see. And so now we have a function to create a SGD optimizer, a function to create an atom optimizer. We have a function to do one-cycle scheduling. And thanks to matplotlib, we can check that it all works.
Yep.
So it's all there.
This is really the power of the abstraction, coming back to one of the earlier questions of, earlier today we started in C, and we were talking about very abstract things like protocols and how things fit together. But when you get those basic things, and this is one of the reasons why learning Swift goes pretty quickly, you get the basic idea, and now it applies everywhere.
Yeah, and here we are doing mix-up. And so now we're in 10. And here we are doing label smoothing. And you see, it's really very similar looking code to what we have in PyTorch. So then by the time we get to 11, other than this hacky workaround for the fact that we can't do control flow differentiation yet, coming very soon, our XResNet, as you've seen, looks very similar, and we can train it in the usual way, and there we go. So we've kind of started with nothing, and Chris spent a couple of decades for us, first of all building a compiler framework, and then a compiler, and then a C compiler, and then a C++ compiler, and then a new language, and then a compiler for the language. And then we came in and...
let me correct you on one minor detail here.
Some people helped you?
Yeah, I did not build all this stuff. Like, amazing people that I got to work with built all of this stuff. So,
cool.
And likewise, like, all of these workbooks were built by amazing people that we were lucky enough to work with.
Yeah, absolutely. So that's all happened. And then let's look at, so like, it's kind of like, thanks to all that work, we then got to a point where 18 months ago, you and I met. You had just joined Google. We were at the TensorFlow Symposium, and I said, what are you doing here? I thought you're a compiler guy. And you said, oh, well, now I'm going to be a deep learning guy.
Well, no, I said, well, deep learning sounds really cool.
Yeah.
And he hadn't told me it was uncool yet.
Yeah. So then I complained about how terrible everything was. And Chris said, I'm going to create a new framework. And I was like, we need a lot more than a new framework. You know, I described the problems that we've talked about with, like, where Python's up to. Chris said, well, I might actually be creating a new language for deep learning, which I was very excited about because I'm totally not happy with the current languages we have for deep learning. So then 12 months ago, I guess we started asking this question of like, what if high-level API design actually influenced the creation of a differentiable programming language? What would that, what would that mean?
And so to me, one of the dreams is when you connect the building of a thing with teaching of a thing with using a thing in reality. And one of the beautiful things about FastAI is pulling together both building the framework, teaching the framework, and doing research with the framework.
Yeah. So, so next time we caught up, I said, maybe we should try writing FastAI in Swift. And you're like, we could do that, I guess. I was like, great.
Well, so I think the one thing before this, I'm like, hey, Jeremy, it's starting to work.
Yeah.
And he says, oh, cool, can we ship it yet? I'm like, it's starting to work.
It needs a high-level API.
Yes.
So let's announce a course where we teach people to use this thing that doesn't exist yet.
And I think I said naively, I like deadlines. Deadlines are a good thing. They force progress to happen.
So then 1 month ago, we created a GitHub repo, and we put a notebook in it, and we got at the last TensorFlow Dev Summit, we sat in a room with the Swift with TensorFlow team, and we wrote the first line of the first notebook. And you told your team, hey, we're going to write all of the Python notebooks from scratch in Swift.
And they basically said, what? What have you got us into? And I think we've learned a lot.
Yeah. So, I mean, to me, the question is still this, which is what if high-level API design was able to influence the creation of a differentiable programming language? And I guess we've started answering that question.
Yeah, I don't think we're there yet. I mean, I think that what we've learned even over the last month is that there's still a really long way to go. And I think this is the kind of thing that really benefits from different kinds of people and perspectives and a different set of challenges. And just today and yesterday, working on data blocks, a breakthrough happened where there's an entirely new way to reimagine it as this functional composition that solves a lot of problems. And a lot of those kinds of breakthroughs, I think, are still just waiting to happen.
I mean, it's been an interesting process for me, Chris, like, because we decided to go back and redo the Python library from scratch. And as we did it, we were thinking, like, what would this look like when we get to Swift? And so we, you know, even as we redid the Python library, we created the idea of stateful optimizers. We created the new callbacks version 2. So that was interesting. But there's also been interesting, I've seen from, as an outsider from a distance, that Swift syntax seems to be changing thanks to some of this.
Yeah, absolutely. So There are new features in Swift, including callables. That's a thing that exists because of Swift for TensorFlow. The Python interoperability, believe it or not, we drove that because it's really important for what we're doing. There's a bunch of stuff like that that's already being driven by this project, and I think there's going to be more. And so like making it so float can default away to nothing, that's really important. We have to do that, and otherwise it wouldn't have been a priority.
So, I mean, so it's still really, really early days. And I think the question in my mind is now, like, what will happen when data scientists in lots of different domains have access to an infinitely hackable, differentiable language, along with the world of all of the C libraries? You know, like, what do we end up with? Because we're starting from very little in terms of ecosystem,
Yep.
right? But like, there are things in Swift, we haven't covered, for example, something called key paths, but there's this thing called key paths which might let us write like little query language DSLs in Swift with type safety.
Yeah, give me all the parameters out of this thing and let me do something interesting to them.
Yeah.
It's really cool.
And so, you know, I guess at this point I'm kind of saying to people is like, pick some piece of this that might be interesting in your domain and
Explore.
over the next 12 to 24 months, explore with us,
Yes.
so that, you know, as Chris said, you know, putting this aeroplane together whilst it's flying, you know, by the time it's actually all the pieces are together, you'll have your domain-specific pieces together, and I think it'll be super exciting.
And one of the things that's also really important about this project is it's not cast in concrete. So we can and we will change it to make it great. And to me, we're very much in the phase of let's focus on making the basic ingredients that everybody puts things together. Like, let's talk about the core of layer is. Let's talk about what data blocks should be. Let's talk about what all these basic things are. Let's not mess with float anymore. Let's go up a few levels.
Float is done. Okay.
Yeah, we can consider float done. But let's actually really focus on getting these right so that then we can build amazing things on top of them. And to me, the thing I'm looking forward to is just innovation. Right?
So
Innovation happens when you make things that were previously hard accessible to more people, and that's what I would just love to see.
So the thing I keep hearing is, how do I get involved? So like, I think there's many places you can get involved, but like, to me, the best way to get involved is by trying to start using little bits of this in work that you're doing, or utilities you're building, or hobbies you have. You know, just try, you know, it's not so much how do I add some new custom derivative thing into Swift for TensorFlow, but it's like, you know, implement some notebook that didn't exist before, or take some Python library that you've liked using and try and create a Swift version.
Try something, write a blog post. Right? I mean, so one of the things when Swift first came up is that a lot of people were blogging about their experiences and what they learned and what they liked and what they didn't like. And that's an amazing communication channel because the team listens to that. And that's a huge feedback loop because we can see somebody was struggling about it. And even over the last couple of weeks when Jeremy complains about something, we're like, oh, that is really hard. Maybe we should fix that. And we do change it. And then progress happens, right?
Yeah.
And so we want that feedback loop, and blogs and other kinds of
yeah, it's a very receptive community,
really
very
great.
receptive team, for sure. Were there any highlight questions that you wanted to ask before we wrapped up, Rachel? Not really? Okay. Well, I mean, let me say this, Chris. It's been an absolute honor and absolute pleasure to get to work with you and with your team. It's like a dream come true for me, and to see what is being built here. And you're always super humble about your influence, but I mean, you've been such an extraordinary influence in how all the things that you've helped make happen, and I'm super thrilled for our little community that you've let us piggyback on yours a little bit. Thank you so much for this.
Oh, and from my perspective, as a tool builder, right? Tool builders exist because of users, and I want to build a beautiful thing, and I think everybody working on the project wants to build something that is really beautiful, really profound, that enables people to do things they've never done before. And I'm really excited to see that.
I think we're already seeing that starting to happen. So thank you so much, and thanks everybody for joining us.
Thanks for having us.
See you on the forums.